industry. I don't think I'm saying something new if I say that all the big companies, small and big, whatever, they are using some form of AI. And this is just Sundar Pichai, who is the CEO of Google, who said a few years ago, and not surprising, that machine learning is a core transformative way by which we are rethinking everything we are doing. And this was mentioned a few years ago. And of course, we know nowadays that this is what's going on. Everything, all companies from Google, Facebook, but also Chinese companies as well, they are using machine learning in a massive way. Well, this is what happened in Google, but the same story can be also seen in other companies. And now we are back to the question, what do we mean when we say that a machine learns to solve a problem? And so I want to go back to the thing that I mentioned before, and that it was also mentioned in the short video clip that we saw. I want now to distinguish the traditional approach to problem solving against the machine learning approach that we use nowadays to solve many problems. Let's see the traditional approach, which I call the traditional programming. If you want to solve a problem under the traditional approach, I'm going to give you an example later. You have to write a program in some computer language. So first of all, you have to think about the problem that you want to solve. You write an algorithm, and then you basically encode that algorithm into a code, into a program, and then you feed a computer with your program, and of course with some data, because you want to solve the problem on some data. So you wait a few minutes or a few seconds or a few milliseconds, and after some time you get an output. Okay, so you have three ingredients here. One is the input data, the other one is the program, and the other one is the output. And of course, you are responsible for writing the program. Now, let's see what happens under the machine learning framework. We still, of course, have the same ingredients: data, program, and output. But under the machine learning framework, we feed the computer with the input data and the desired output data, which means with examples, and we let the computer to produce a program. So here is the main difference. Under the traditional approach, you are responsible to writing the program for solving the problem. Under the machine learning approach, it will be the computer that will give you the program for solving your problem. Now, let's see a concrete example just to understand a little bit better what I mean by that. Suppose that, and this is a problem which is very difficult indeed, and nowadays we solve it using machine learning. But suppose you're working for a company, for example, and your boss comes to you and say, look, we need to build a program, an algorithm, which takes as input a picture and tells me whether in the picture there's a cat or not. Okay, we want to build a cat recognizer. For some reason, we feel that we can make a lot of money with this algorithm and blah, blah, blah. Okay, so under the traditional programming approach, you sit down at your desk and you start thinking about the problem. So you want to build a cat recognizer, and then you think about cats. You have to become an expert in cat recognition. And for example, you think about the problem and you say, okay, a cat usually has 2 eyes, it has 4 legs, it has 1 tail. So you write down rules, and these rules come out from your mind, right? Because you are becoming an expert in the problem, and since you are an expert in recognizing cats, you basically write down explicitly all the rules. And that's your program. Okay, this is of course a caricature of a cat recognition system, but just to give you the basic idea. So this is you trying to solve the problem, and after a while you come up with the program that solves the cat recognition problem. Then you go to your boss and say, look, I've found the program, here you go, now it works. And then you get a new picture of a cat, and then you feed the computer with the new picture and your program, and the computer, of course, tells, yeah, there is a cat here. Now, let's see how we can solve the very same problem using machine learning. Using machine learning, we forget about becoming experts in cat recognition because it's too difficult, right? It's not just a matter of having two eyes or having four legs, because the pose of the cat might be different. Here, for example, I only see two legs. I don't see three legs. There might be situations where I don't see the tail. For example, here I don't see the tail. It's a difficult problem. It's not easy to come up with a number of explicit rules for solving the problem. But of course, we all know if I'm given a picture, I will tell you whether there's a cat or not. So that's easy. I don't know why. If you ask me, how did you make it? How can you tell me how did you recognize a cat in the picture? Of course, I cannot tell you. Nobody can tell you how, but I can do it. And the reason why I cannot tell you is because something is happening in my brain under, subconscious level, I would say. And so I'm not aware, I'm not conscious of the activities in my brain, which allows me to tell that here there is a cat or here there is no cat. And so I cannot explain why, but I can do that. So why don't we build what we call a training set, which consists of a number of cats and also a number of non-cats. And then I feed the computer with this training set, and using a learning algorithm, and that's the main business, our core business in this course, I will let the computer find and build a cat recognizer. So after this learning process, once I'm given a new picture, I will feed the program that the computer has generated with a picture, and the computer hopefully will tell me whether there is a cat or not in the picture. Now, what is our role as humans or as a computer scientist here? Well, there are two parts. One is the development of the learning algorithm. We have to build this learning algorithm. Sometimes the algorithm is already available, you download it, and then you can use it. And this is very convenient. Sometimes it's not. So you have to develop your own algorithm. And also, of course, the role of humans is also to develop the training set. Although nowadays there are more sophisticated techniques, but at least there must be a human in the loop here, which allows you to build in the first place the training set. So a set of instances which contain cats and non-cats that the learning algorithm will use. Now, imagine how flexible this approach here. Just let's try to think about this. You want to solve a cat recognition problem. You are not forced to become an expert in cats, but you have to become an expert in machine learning. That's true, of course, but machine learning is more general. And provided that you yourself or someone else is able to provide you with the training set, then you are done. Now, imagine how flexible this approach is. Suppose that tomorrow, once you have solved the cat recognition problem and your boss is so happy that now your company is making a lot of money with this cat recognizer, imagine that a new problem arises. So after you have solved the cat recognition problem, the boss comes to you and say, look, now we need to find a system which detects dogs, no longer cats, or cars, or bicycles, or snakes, or whatever, right? Now, under the traditional approach, let's go back, you will have to become an expert now in dog recognition or in, I don't know, car recognition or in bicycle recognition and so on and so forth, which makes a lot of time. But under the traditional machine learning approach, at least ideally, you can still use your learning algorithm. And the only thing that you have to do is to create a new training set. Instead of cats, now you will have to create a training set containing dogs and, of course, non-dogs. And then everything will remain the same, and then you are done. So you see, we are shifting the attention from the development of a learning algorithm or a specific problem solver to the development of sufficiently large training sets. That's the basic idea behind machine learning, a very general approach that works on very difficult problems and that allows us to solve different families of problems, basically using the same framework. Okay, I think we should make a break now, just as a completely new paradigm to problem solving. And as I mentioned before, this is really a game changer. And not surprisingly, this approach now has become so popular in solving a variety of difficult problems. Of course, machine learning is a purely data-driven approach. So the assumption that we are making when we are using machine learning is that we have to have access to data. And now I want to mention one thing that my old friend Nello Cristianini, who is a professor of artificial intelligence in UK, a few years ago wrote about the lesson that we learned in artificial intelligence. As I mentioned before, the history of artificial intelligence, which goes back to the 40s, is, in some sense, this is the prehistory, although officially the field was created in the mid 50s. This history tells us something that is very important. That after more than 70 years of work in the area or more, we learned a powerful lesson that data can be stronger than theoretical models. And contrary to what was happening a few decades ago in the field of artificial intelligence, people didn't care about data. Maybe because there weren't too much data around, because we should keep in mind that now we can use data because we have them. Some 20 years ago, data were not available, or there are, were very small data sets and we cannot use it. And so the lesson learned was that by having a large collection of data, sufficiently large, purely data-driven approaches are much more powerful than model-based approach, such as expert systems or those based on explicit rules. And well, this is an old picture. Once again, I should update that, but the situation, of course, it's already impressive here. Talking about data, now we can use machine learning, well, for two reasons. First of all, because we now have, thanks to the internet, a huge amount of data available for us. And here is just a snapshot what happens on the internet in 60 seconds, in just 1 minute. And of course, here, this is an old picture. This goes back to 2016. Now it's even worse, or even better, of course, depending on your point of view. YouTube, let's take YouTube. In 1 minute, about 3 million video views. WhatsApp, which is our equivalent. You have WeChat, we have WhatsApp. More than 20 million messages in 1 minute. And once again, this happened a few years ago. So now we can use machine learning. A few years ago, we could not. And of course, we worked in machine learning, but the results were not so impressive as we have nowadays. And the results nowadays are so impressive because we have access to a large amount of data on the one hand, and on the other hand, we have very powerful computers that a few years ago we didn't have. So the combination of massive data sets and very powerful computational resources with maybe thousands and thousands of GPUs and whatever, the combination allowed us to now basically use machine learning almost everywhere. But there's even something which is deeper than that. And then we will start talking about more technical stuff. And a few years ago, there was a magazine paper that was written by Chris Anderson. The title of the paper was The End of Theory. And basically, the take-home message of this paper, which has been discussed a lot, has been a very controversial paper, was that we should go beyond the field of machine learning. He was basically saying that we should rethink the way in which we do science. His main point was that we have been doing science for centuries. Think about physics or chemistry or biology, using a purely model-based approach. So we think about some model, and then we see whether the model works well in practice. The whole field of physics, but also chemistry, biology, economics, and many other sciences are constructed in this way. And so he was suggesting, since nowadays we live in a society, in a world where we have access to huge amount of data, we should rethink the way in which we do science. In other words, we should try to invent a new purely data-driven approach to science. And that's in this controversial paper, he was pointing out that the availability of huge amount of data will force us to rethink the way in which we build our scientific models. That's the reason why the title of this paper was The End of Theory, because he was claiming that we're going to move towards a society where theories are no longer purely model-based, but are created by data. Now, of course, this is a controversial issue, and it's been debated a long time whether this is correct or not. But I just want to mention what is the impact that a purely data-driven society is having on all aspects of our life. Okay, now let's go into a little bit into the details of machine learning. And basically here we are also talking a little bit about the content of this course. There are at least, but there are more actually. Here it's a subset. There are at least 3 kinds of machine learning problems. One is called unsupervised learning. And basically a typical example of unsupervised learning is clustering. In this approach, we are making the assumption that all the available data are unlabeled, just raw data, just collect a bunch of data, and that's it. The opposite of this approach is supervised learning, where we make the assumption that we have collected a large number of data, and these data are labeled. So you see the distinction between these 2 approaches. On the one hand, supervised learning are making the assumption that all the data that I have at my disposal are labeled. For example, going back to the cat recognition example that I mentioned before, we collect a large collection of images, and together with each image, there is a label. This is a cat. This is a dog, this is a car, this is a snake, this is an elephant, and so on and so forth. And if we do so, this is called supervised learning. Otherwise, if I just download, say, from the internet, say 1 million images without any label, then we are talking about unsupervised learning. So these are 2 opposites, 2 extreme situations, I would say. In between, there is a third option, which is called semi-supervised learning. Well, we are making the assumption here that you collected a large number of data, only some of which have been labeled, but most of them are not. And the goal is, how can I use the unlabeled data to build, say, a cat recognizer or a dog recognizer, and so on and so forth. Now, there are more kinds of machine learning, though. I only mentioned these 3 because we are going to focus mainly on these 3 approaches in this course. But let me also mention reinforcement learning, which I didn't write here, which is, of course, another very important area in machine learning, which is especially important in the field of robotics, but also in other fields. In reinforcement learning, we imagine that there is a learning agent, learning machine, which makes some decisions, and there is an external environment which provides, in a continuous loop, I would say, feedback about the quality of the decision taken. So imagine this loop: the learning machine or the learning agent provides the external world with some decision or with some action. The external world will provide a feedback whether the response was correct or not. And so in this loop, the system will learn how to solve a problem. The difference between this and supervised learning or unsupervised learning is that here is a dynamical thing. So you imagine a system which gives you a response, you tell the system whether it was correct or not. You basically give a reward if the answer was correct, and you give it a punishment if it was not correct. And so in this loop, the system will learn. This is called reinforcement learning. And there are also other areas such as self-learning, which, by the way, is being used by ChatGPT and so on and so forth. Now, in this course, we're going to focus mainly on these three kinds of machine learning problems, which are the most popular ones around. And this is the content of the course. That's the road ahead. In particular, we will start talking about supervised learning, and we will be talking about neural networks in particular, and I will be talking about the kinds of neural networks that were common until the 90s. And then we'll be talking about another class of machine learning algorithm, which is support vector machines. Remember, machine learning is not just deep learning. There are also other algorithms around, and in this course, you will learn about other algorithms as well. And then we will be talking about deep neural networks. In particular, we will be talking about a class of deep networks, which are called convolutional neural networks, which are extremely popular and powerful in fields such as computer vision, for example. Then we will be talking about the other branch of machine learning, which is unsupervised learning. So here, remember, we are making the assumption that we don't have any label. And I will be focusing on two very popular class of clustering algorithms. One is spectral clustering, the other one is dominant set clustering. And also the course will be focusing on some applications, and we will be talking about a few computer vision applications, in particular image classification or semantic segmentation, object detection, tracking,